Now that we have a few more derivative rules under our belt, namely the product rule and quotient rule, we can include some more trigonometric derivatives. So we already know the derivative of sine and cosine, so here's some examples for those, and then we'll learn about the next 4 trigonometric functions derivatives. So let's start here. So in this first one, f of x equals negative 6x cubed sine x minus x plus 1. Well, this right here is a product. It's also a sum and difference, so we could take the derivative of this, separate from this, separate from that. So here we go. F prime of x will equal, so think of this first function, second function. So I'll take the derivative of the first function, so that's going to give me negative 18x squared, and that'll be times the sine x, plus, or in this case minus, 6x cubed, times the derivative of sine is cosine. So there's that piece. Then we have to still take the derivative of the rest of this, but separately now. The derivative of minus x would be minus 1, and the derivative of 1 would be 0. Now I don't have to write the plus 0, so here is my derivative. How about this one here? Right? Y equals sine x over cosine x. That's a quotient. So if I were to apply the quotient rule to that, y prime would be the derivative of the numerator, so the derivative of sine, I'll write it out. Derivative of sine times the denominator, cosine, minus the derivative of the cosine times the sine, all over the denominator squared, so cosine squared. So what happens here? Well, derivative of sine is cosine, so this piece right here would be cosine x, then times this other cosine x that's sitting right there, minus the derivative of cosine would be negative sine, so actually this becomes plus sine x times this other sine x, all over cosine squared. Okay, well, we can simplify this. The derivative is done at this point. This is the derivative, but we should simplify our answers as much as possible. Well, this is cosine squared. This is sine squared. So I would have cosine squared x plus sine squared x over cosine squared x. But we should know that cosine squared x plus sine squared x equals 1. So this is 1 over the cosine squared x. But we should also know that 1 over the cosine is equal to the tangent. We have this identity. It says 1 over cosine x, equals secant x. I think I just said tangent a second ago. It's not tangent. Secant x. So then 1 over cosine squared should be equal to secant squared x. So this derivative is equal to secant squared, or sorry, the derivative, I should say. Sorry, that was terrible. The derivative of y is equal to secant squared x. Now, this brings us into the next thing. We should also know that sine x over cosine x is equal to the tangent. So, if y is equal to the tangent of x, okay, which is what this is, okay, then the derivative of that, y prime, should equal secant squared. And so what you just saw is basically a proof for how you find the derivative of the tangent of x. So here are your 4 other trigonometric functions besides sine and cosine. We just saw that the derivative of tangent is equal to secant squared. And now the derivative of cotangent x is equal to negative cosecant x squared. The derivative of secant x is secant x times tangent x. The derivative of cosecant x is negative cosecant x, cotangent x. The proof, again, we saw this first one. The proof for cotangent is very similar. We would write cotangent as cosine over sine, as opposed to tangent, which is sine over cosine. And we would just apply the quotient rule, and we would end up with that negative cosecant squared, just like we got secant squared. The one for secant and cosecant, they're very similar as well. I'll just do one of them. I'll do the secant one. So the trick here is to use an identity first. So we have secant x, that's what we're trying to take the derivative of. I'll write it as 1 over cosine x and take the derivative of that instead. And then that'll tell me what the derivative of secant is. So then y prime, if I use this, would have to apply the quotient rule. The derivative of 1 is 0 times the cosine x, minus 1 times the derivative of cosine x would be minus sine x, over the denominator squared, so cosine squared x. Well, 0 times this, that's gone. Negative and negative would give me a positive. So I'd have positive sine x over cosine squared x, which I'll write then as sine x over cosine x times 1 over cosine x. So this is still cosine squared in the denominator. But here, this is an identity that sine over cosine equals tangent x. And 1 over cosine equals secant x. So tangent times secant, or secant times tangent, however you want to write it, they're multiplied so the order doesn't matter. But the derivative of the secant is the tangent times the secant, or secant times the tangent. And this one would follow basically the same way. You'd write this as 1 over sine, and then follow the same procedure. What I highly suggest you do is that you memorize these 4 trigonometric derivatives. Index cards, great way to go. Make some index cards, put this on the front, put this on the back. Quiz yourself. You don't come across these as often as sine and cosine, so it's going to be harder for you to remember them. So having the index cards and quizzing yourself periodically would be a good way to memorize these. You will make your life so much easier throughout all of calculus the sooner you get all these rules memorized. Okay? And don't just rely on having to look them up all the time. And now here we'll get some practice on using these new derivative rules for the trigonometric functions. So very simply, here's y. It equals x minus tan x. So since it's a difference, I could take the derivative of each one of these functions first. And as long as I know the derivative of each one, this is very easy. So y prime will equal the derivative of x, which is 1, minus the derivative of tangent, which we just found, is secant squared. And so you can leave your answer like that. However, if you know 1 minus secant squared is an identity, and we can say that that's equal to negative tan squared. While it's not completely necessary to do that, it is simpler, but either one, there's your derivative. But you need to know the derivative of tangent x to be able to do the derivative of this function. All right, let's go to B. X times secant x. Now this is a product, so I'm going to have to apply the product rule. In applying the product rule, I'm going to also have to take the derivative of both x and secant x. And if I don't know the derivative of secant x, I wouldn't be able to do this. But we now know that. So y prime would equal, and I'll write this out just so we get used to it again, the derivative of x times secant x plus the derivative of secant x times x. Well, again, if you know each of these derivatives here and here, this is very easy. Y prime would equal 1 times secant x plus the derivative of secant is secant x times tan x. So we'll have the x times secant x tan x. I just like putting this x up in the front. Okay? And we could leave our answer like that. Another option is we could say, well, there's a secant here and there's a secant x here, so I could factor that secant x out. I could write this as 1 plus x tan x. That's not really simplified necessarily, it's just factored. Either of these answers, this one or this one, would be acceptable. All right, let's look at this third one. Okay. So here, it's just a difference. So we can take the derivative of this function separate from this function, but each one is one of those trig functions. We would need to know the derivative. So to find the derivative of c, so y prime would be the derivative of cosecant, which is negative cosecant x cotan x, minus the derivative of cotan x, which is negative cosecant squared, so then this would become plus cosecant squared x. And again, we could leave our answer like that, or we could factor out a cosecant, and I could write the answer as cosecant x minus cotan x. You know, there's still leftover cosecant here, then here there'd be a negative cotan left over. I've reversed the order, so I put the negative on the back. But either way, that this is your derivative or this is your derivative, but you couldn't do these unless you know the derivative of those functions. So you're going to want to commit those to memory. So we've talked about higher order derivatives, second, third, fourth, fifth derivative, etc. And we've talked about trigonometric functions. So here's a question for you. What is the 103rd derivative of sine x? Now, in order to find the 103rd derivative, I really would need the 102nd derivative. In order to find the 102nd derivative, I would need the 101st derivative, etc. Right? Because to find each derivative, you need to know the one before it. But one thing we should understand is that there's a pattern to derivatives sometimes, specifically here with sine. So let's look at sine. F of x is my sine function. The derivative is cosine. The second derivative, which is the derivative of cosine, would be minus the sine function. Now I could just keep doing this until I get to the 103rd derivative. But it's not really necessary. There's a pattern happening here. Let's look at it. We're almost there. Third derivative is the derivative of negative sine, which would be negative cosine. The negative is a constant multiple, and the derivative of sine is cosine, so that would be this. Now let's look at the fourth derivative. The fourth derivative, which once we get the fourth derivative, remember we have to put it in parentheses, of x, because we stop using these tick marks, because that would get ridiculous, is the derivative of negative cosine. Well, the negative is there. Derivative of cosine is the negative sine, but that would just give me the sine function. And I get back to where I started. So then the fifth derivative would be the cosine. The sixth derivative would be negative sine x. The seventh derivative would be negative cosine x. And we get back to the eighth derivative to get sine again. So you see, it just keeps circling back over and over again. So the fourth derivative, the eighth derivative, the 12th derivative, the 16th derivative, they would all be the sine function. So then let's use that to help us find this. So we should know at least that the 100th derivative would be the sine function, because it's all multiples of 4. 4, 8, 12, 16, 32. Well, there's between 16 and 32 would be other ones, but 20, 24, etc. But anyway, the 100th derivative would be sine. So that means the 101st derivative, the 102nd derivative, and the 103rd derivative we should be easily able to know as well. This would be the same thing as basically the first derivative. This would be the same thing as the second derivative. This would be the same thing as the third derivative. So the 103rd derivative for sine should be negative cosine x. And so we didn't have to actually find 103 derivatives to get the answer for this. Some functions where their derivatives don't have a pattern to them, you may have to do that. I mean, it would be ridiculous, but you may have to do that. But for something like this, once you see a pattern and our derivative for sine has a cyclical pattern where it gets back to where you started again, we could then stamp out that pattern until we find where we need to be.